Hey, welcome back, physics fans. Welcome to perhaps one of our last lessons of this chapter of space and energy. But here we're going to just take a look at we're on the Earth. And we have this guy in a half pipe, kind of a weird one. I've shaped it differently. But anyways, you can see his kinetic energy and potential energy swapping. And at any point, we could add up the blue and add up the green, and it gives us the total, and the total is staying the same. That's kind of the key point, the conservation of energy here. As it goes down here, we'll be moving at its fastest, so kinetic will be the most. We're measuring our 0 point from this dotted line here, so we're just barely any potential energy here. But as he goes up and slows down to the top there, as he slows, kinetic is practically zero, potentials there. Okay, we've done this before. Okay. We need to understand some concepts here before we get going into this energy thing. They're not easy concepts, but let's just talk about that. Convergence series. Okay, convergence. Weird term. Sometimes people use it, and they don't know what they're really talking about, but let's hear it. Here's a few examples of convergences and stuff like that. So if I take the number 1, then half, plus a third, plus a fourth, plus a fifth, plus a sixth, and I go on for all the way up to infinity, what happens to the sum? So that the plus sign is there. So it's not listening, but I add the next one, and I add the next one, and the next one, all the way up to there. This goes off to infinity. So you keep on thinking that if I keep on adding things on top of each other, always, it adds up to infinity if I keep on adding something. So I take a bucket and I keep on putting drops of water into it. Eventually it'll overflow. And eventually, if I kept on adding drops, I'd fill up the whole Earth, right? You keep on going, you keep on adding things. It seems to go to infinity, especially if I go for infinity. But it's not always the case. Sometimes you can, if you add up numbers here, here we go. 1 plus 1 plus 1/2. I don't know what that series is. That's factorials, I see. Okay, or 1 1/4, 1/9, that's 1/16, 1/25, 1/36. You see the pattern there. I'm squaring it. This doesn't go to infinity. As I go forever and ever and ever and ever and ever, if I could go up to infinite, it becomes a solid number. It doesn't go any higher than that. So if I take like the number 1 plus a half plus a quarter plus an eighth plus a 16th, and kept on going forever and ever and ever, it doesn't become infinitely large. This just becomes 2. So if I go forever and I keep on adding things forever, it doesn't have to go to infinite. It can be a fixed number. Okay, this is kind of like taking one pizza and then taking a half a pizza and then adding a quarter more and then adding an eighth more and adding a 16th more and adding it, and you keep on going, you're going to end up with 2 pizzas. Relative measurement. Okay, we need to understand this little term here. It's not hard here. Okay, here's the front wall of a house and the back wall of an apartment and stuff like that. A nice one. But what happens if you were only able to measure distances from, let's say, the front wall? Okay, and that's not too hard. If I was going to say how long is this bed, it'd be easy. You would just measure from that wall and down to there, and the length of that line would be the length of the bed, because I'm measuring from the front wall, and that's okay. Right? You're measuring from the front wall. I can't paint. I need to be bigger here. So measuring from the front wall to there, it's easy because I can measure from the front wall and I get that distance. But what happens if I wanted to know the width of this table? I want to know that width, but I can only measure from the front wall. Well, a lot of people will not have an issue with that, right? You will just go, I need this distance and this distance, and I subtract them. Okay, did you get that? Maybe not. You take that distance and that distance, and then you subtract them, you'll get the distance that you want. right? Just the scale, you want your cat and weigh how heavy your cat is, but your cat won't stand on the scale. Well, you hold your cat and weigh yourself with the cat, and then weigh yourself without, and then subtract it. And then you get the length of your cat. So that's how you do your TV length, right? The width of that, you'd measure that distance, and you'd measure that distance and subtract it to get that. Okay, simple concept. The next one is Newtonian gravity and infinite distance. Okay, so we just learned about Newtonian gravity, although it was a relatively simple. I might have forced you into it, but we had the force of gravity is equal to G mass of object 1, mass of object 2, and r squared. And as we pull these objects apart, there's still going to be a force of attraction between them. So we have M1 and M2, and we pull them apart. As we go forever and ever and ever away, or go farther and farther away, there's still always a force. Always a force. I can go to Andromeda, another galaxy, and move over to there, and you'll still have a force. There's always a force pulling it in. Okay, always a force pulling it in. Now, that's infinite distance. There's always a force. But it goes as the square, inverse square. So let's just show you a graph here. The graph kind of looks like this. It's an inverse square relationship. And a lot of things in physics, light, sound, all kinds of gravity, all work as an inverse square. Okay, so understanding this graph would be a little helpful, right? If you're taking a certain value, if you go twice as far away, it'll be 1/4, inverse square. So 2 times inverse and square is 4. 3 times is inverse and square is 16th and 16th. So gravity just drops off really quick. In fact, what happens if you had an apple at the surface of the Earth and you went to 2 times away, and 3 times away, and 4 times away? How much would it weigh? Okay, so if an apple weighed 1 Newton at the surface of the Earth, if you went 2 distances away and held it here in space, what would its weight be? It'd be 1/4 of a Newton. And if you went 3 distances, again, measured from the center of the Earth, 3 of these radii away, you'd be 1/9. So it doesn't go to 0. It never goes to 0, but it gets really small, really quick. Right? A quarter, if you just go, and then 16th. So if you went 10 distances away, it'd be 1/100th. Okay, it just drops off rapidly. Work is the area under a force distance graph, and that's how much energy it requires. Okay, so we need to find the area under that force distance graph. So we were just on a graph there. How much work would it require over the year to lift it? Okay, MGH, we'd like to use MGH, but the force is changing. Beforehand, when we lifted up an object, there's the ground, and we took an object and we lifted it up to here. We used that as our H, and we went, the work required was the change in potential energy, and that was just MGH, and G didn't change. So we could just easily do this, because this is the force, and the force didn't change. So on the force distance graph, it was a flat line. The force was the same from the ground at 0 to the ground at H, and this area was just MGH, and that's why the work was that, and that's why the change in potential energy was that area. But now, what happens when we have a graph that looks like this? We have to, let's just take that over, boom, and go to here, and how do we calculate how much work it is to lift it from 1 Earth radii to 2 Earth radii? So this distance here is just going to be 6.38 times 10 to the 6th. So if you just went mg and this h, you would be wrong. That's not the constant force. Because it's not that. And that's what you'd be calculating, all that box. But we want to find out the area under this. Oh, goodness. How do you find the area under that? How do you find the area under that? Okay, interesting. Because G changes. And G is just Gm over R squared. And that's why it changes. The R changes significantly. So how do you do it? Well, let's just understand how to do that. So we want to find this area of this red, right? If we're going to take it from radius R all the way out to 10, we want to find out all that. But how do you do that? Well, we have to be able to set a 0 point somewhere, right? We have to set where the potential energy is 0. And interesting enough, when you find this area underneath, that is going to give you negative G mm over R. But this is interesting. This is relative. Where is the 0? And if we go all the way out to infinity, that is when this term becomes 0, or the force becomes 0. Gmm over R squared. When we put R as infinity, then this is over infinity squared. That's 0. So when the force is 0, then the potential energy here will be 0. So they set the potential energy to be 0 at infinity. And then as you get closer to the object, you lose energy. You lose potential energy, right? That was the old, this guy. As you start coming back down, let's slow it down. As you start coming down, you lose energy. But this is not measuring 0 to be at the farthest height you go away. Let's just do that. And I will slow it down and stop it when he's right at 0. There we go. Sound effect necessary. There we go. So once I hit play for a second, his total energy becomes 0. His kinetic is 0. His potential is 0. That's the importance. And as he goes, his potential becomes negative. So from the point that we call infinity, we measure the 0 point, and as it comes down, so potential energy is going to always be negative because you can't go above infinity. So interesting term. That's why there's a negative. And this is measured from infinity. Where's R measured? From infinity? No. R is measured from that mass to that mass. That's the distance between them. So the mass, if you're 1 R away to 2 R away, how do you do that? We want to know the work it takes to go from 1 R to 2 R. Well, that's where that relative distance was. I said here's the wall and here's the part. We want to measure this, and then we want to measure that, and then subtract them. So because the graph for this guy is all of this, all of that distance, and the graph for the shorter, or for the other one is this, all the way up to infinity, but what we want is just the area there. So you have to take all the area and subtract all the area out from that point. So if we want just this, we have to calculate all of it and then calculate all of it. Now, why is that? Because this formula only counts relative to infinity. So we have to do it. We always measure from the outside wall. That's this formula. We always measure from infinity. And you think that if I keep on adding areas up, I get to an infinite number, though that was the convergence. I don't get to an infinite number. I get to a rock solid number. Here's a bunch of physics questions from a different person's workbook. And notice there's a term here, relative to zero at infinity, RTZAI. So they're measuring that the potential energy is zero at infinity. Okay, so let's just take a look at these two questions. Let's do number 6 first. Find the potential energy relative to zero at infinity of a 10.5 kilogram mass that is 1.5 meters away center to center from a 5 kilogram mass. So there's our two masses, and this distance here, center to center, is 1.5 meters. This mass is 10 kilograms, 10.5, and this is 5 kilograms. Now, if I take this off to infinity, its potential energy is zero, way out at infinity. And then, so when I let go of it, it falls to, and we want to know what its potential energy is there. Well, the potential energy there is given to negative G M over R. And that is going to be negative 6.67 times 10 to the negative 11. And one of the masses, 10.5, the other mass, 5, and the separation distance of the two masses, which is 1.5. You pull up our calculator, and we get 6.67 e to the negative 11th times 10.5 times 5 divided by 1.5. Boom. So we get an answer that they suggested. 2.3345 times 10 to the negative 9th joules. So that's how much potential energy is lost. So if it fell from infinity, that's how much potential energy is lost. Okay, now here comes the eye-opening question. I love this question. Or anything like it. Lots of them on provincial exams. Okay, here it is. A 1,200 kilogram mass is released from a height of 4,500 kilometers above the Earth, and it falls to the Earth. And no external forces are acting on it. There's no friction. The system energy is conserved. Okay? A, what is the work energy equation? So beforehand, nothing's moving. This guy has potential energy with respect to infinity. There it is. And it has no kinetic energy. And when it's about to hit, it still has potential energy with respect to infinity. And it's also going to have kinetic energy. So it's going to have potential energy and kinetic energy. Because we're never at the infinite point. Doom, doom. So what is its final potential energy? Okay, and find the PE when it reaches the Earth. Oh, it's the initial and reaches. So we want to find out the potential energy when it's initial. So it's negative G M over R, and that's going to be 6.67 times 10 to the negative 11th, right? And then we need the mass. And now we're going to have the mass of the Earth, and we're going to have the mass of that object, 1,200, and then we need the distance separating it from the center to that. Okay, so I need to work down below because it's getting awkward. Here we go. So it'll be 6.67 times 10 to the negative 11th. The mass of the Earth is 5.98 times 10 to the 24th. The mass of that object is 1,200. And this is going to be a negative. And we're going to have the radius, the distance away, will be the radius of the Earth, 6.38 times 10 to the 6th, plus 4.5 times 10 to the 6th meters, right? This says kilometers, but we have to go to the meters, so it's not 10 to the 3, but 10 to the 6th. Okay, so let's plug that in. I'm going to hit an equal sign when I do the numerator, because it'll speed up our calculations for the second part. 6.67 e to the negative 11th times 5.98 e to the 24th times 1200. That's the numerator. 4,786 times 10 to the 17th. And we have to divide it by bracket, because we're going to do the addition. 6.38 e to the 6th plus 4.5 e to the 6th. Close the bracket, and whatever the denominator was, it becomes, I'll put the negative in now, negative, and gosh, that's pretty close to 4.4, 4.3993 times 10 to the negative 10 to the 10th joules. That's a lot of potential energy. Nice. And that's where it begins with. So that's PEI. And now we do the same thing for the next one. Okay, let me just kind of cheat here. Oh, I don't want that number. I want copy. Down. Put it down here. And now I want to do the whole thing, but not with height. So that's why I kept the numerator the same. And so take that numerator there and divide it by just 6.38 e to the 6th. And we get negative 7.5022 times 10 to the 10th. And that's the potential energy final. So when I take this number and subtract that number, this is final minus initial. We're going to get a change in potential energy that's going to be negative. Okay, so let me just zoom out here a bit. So the change in potential energy is, oh, did I get the two numbers right? That's right. So the change in potential energy is going to be negative. That means potential energy is going to go down. That means kinetic energy has to go up. So the potential energy final minus potential energy initial. So how do I do that here? Let's just get this in here. I'll type this in. Negative, whoops, clear. Negative 7.5022 e to the 10th, subtract a negative 4.3993 e to the 10th is just going to equal negative 3.9 3.1029 times 10 to the 10th. So that's the change in potential energy. So that means the kinetic energy has to be, kinetic energy final has to be positive 3.1029 times 10 to the 10th. And that has to equal 1/2 times the mass, which is 1200, times v squared. So I multiply this by 2 divided by 1200, and then I square root it. Oh, gotta make sure it's a negative and a positive in there. So I got a negative, the answer is that, and now square root that. Also square rooting the negative will give me an error. V is equal to 7191 meters per second. Nice. So that's how fast it'll hit. That's cool. Okay, that's good. That's it. That's the velocity that it'll hit with. Now, if you're on the planet and you throw it up with that velocity, how high will it go? It'll go 4,500,000 meters high. Because at that point, its kinetic energy becomes zero. And its potential energy is there, and it stops. That's pretty cool. Okay? So you can now reverse it, right? If you throw it up with that energy, we now know what height it goes to. What potential energy does this have? It has a negative 4 point, the final is on the ground, whoops. It has a negative 7.5022 times 10 to the negative 10 joules, or positive 10. So if I take this object and give it positive, that much kinetic energy, it's going to go. But how high does it go? If I give it that much kinetic energy, it's going to lose kinetic energy, become potential, go potential. But just take a look at it. We have the potential energy plus the kinetic energy, and the potential energy initial was this negative 7.5 times 10 to the 10, and I gave it the kinetic energy of 7.5 times 10 to the 10, so its total energy would be 0. What does that mean? What does that mean? The total energy would be 0. When would it lose? So here I gave it so much kinetic energy when it's near the Earth, and potential energy was negative, and then when it reached this point, boom, the total energy is still 0, but also potential energy 0 and kinetic. So when does it stop? When the potential is 0. When is the potential 0? At infinity. So this has 0 joules. So if I give it this much kinetic energy, that means it's not going to stop. It's always going to have kinetic energy until it reaches infinity. And it'll never reach infinity because it takes an infinite amount of time. So it's going to lose and lose and lose. Okay, let's just take a look at this one. So this is when the total energy is negative. You give it so much kinetic energy and potential energy, and sometimes in universities they go U because there's too many P's already for power and momentum and stuff like that. So they give potential energy U. So if I give it so much potential energy, well, I mean the potential energy is fixed there compared to infinity, but enough kinetic energy, but not enough to make a total energy 0, then eventually the object comes to a stop. Boom. It comes to a stop because the potential energy becomes, boom, that much. So let's just, again, it just flies and eventually stops and comes around. Why does it stop? Because it runs out of kinetic energy. But what happens if you don't run out of kinetic energy? You give the total energy as 0. So you give enough kinetic energy and potential energy And then, so it just slows down, keeps slowing down, but it'll never stop because the kinetic energy doesn't become zero. So if the kinetic energy doesn't become zero, then what happens? You never come home. And that is called the kinetic energy. What speed would that be? Sometimes to throw it infinitely far away, you need an infinite speed. No, you don't. Interesting enough. So its kinetic energy would equal 1/2 mv squared, which is going to be 7.5022 times 10 to the 10th. And that's going to equal 1/2 mass of this object was 1,200 kilograms and v. So let's just plug this in. And I'll take that number from above, if I can find it. There it is. Take that number, multiply it by 2, divided by 1,200, and then I have to square root it. Goodness gracious. That's not an impossible number, but that's a big number. The velocity would be 11,182 meters a second, or 11.18 kilometers per second. And if I throw something up at that speed, it's not going to stop. Therefore, it's going to escape the Earth. If I threw it up at 11.00, it'll finally stop somewhere because it won't have enough potential energy. It'll still have a negative potential energy. When I add these two things together, it'll be a little less than this. And when I get a negative number, and then it'll just finally reach here and stop and come back. So I have to get up to the escape velocity for it to escape. Okay, and that's the definition of escape velocity. Well, it is. How do I get to it? I make the potential energy equal to its kinetic energy necessary. The potential energy at the initial has to be the kinetic energy at the initial, because when I add them together, they have to be, but one's going to be negative, one's going to be positive, because I have to take that. So that's why I could get rid of the negative, because when I add them together, they have to be 0. I don't know if you get that. Because when I add them together, I have to get 0. So when I put it over there, one becomes a negative. And that cancels that negative. The mass of the object doesn't matter. And then, so V is going to equal the square root of 2gm of the Earth over r. And r is how far away you are from the Earth. So if you're on the radius surface of the Earth, then you have to use the surface of the Earth. That's how far away the object is. And that gives us the escape velocity, v escape. Beautiful. That's the escape velocity. So if I took something from infinity and dropped it, what speed would it hit the Earth at? That escape velocity. 11,182 meters per second. Right? So something comes in and passes by the Earth, and it's going faster than this. It came from outside our solar system, outside our galaxy, probably. Well, there's different numbers that you have to calculate, but that's good. I love it. That's how to calculate the escape velocity using this formula. Did you notice that this looks very similar to a formula that we had last lesson? Orbit. Orbital velocity is gm over r. So the only difference is a 2 in there. But how they're derived, this is all on energies, and this was all on forces, the gravitational force and the centripetal force. Interesting that you start from different places, totally different places, but you end up with very similar looking formulas. Anyhow, sorry, I've rattled on for way too long. Let's maybe put up one more jingle there to expand our knowledge. No, maybe I'll go on just a smidgen more and we'll get to it. And we'll finish it all. So, this is the escape velocity. And the more massive the object, the larger the escape velocity by the square root of that mass. Right? If I doubled or quadrupled the mass of the object, then I'd double the escape velocity. And I keep getting the more massive objects. What's the escape velocity from the sun? It would be a lot harder, a lot higher, because that sun is 2 times 10 to the 30th. But I wouldn't want to be that close to it. I want R to be quite far, because that mass is huge. That's like a million times bigger than the Earth. So it'll be the escape velocity will be 1,000 times bigger. But did you guys know that there's a speed limit in space? And it's called the speed of light. Nothing can move faster than that. And that is 3 times 10 to the 8th meters per second. Oh, well, goodness, that's a lot different than this times 10 to the 4th. That's huge. But what happens if we did put the speed of light in there? Then we can calculate the mass. What mass would that be? What mass would that be? Well, that would be the mass of something that it can't escape. Because if you need it faster, you need that speed, you can't get there. And if you can't escape that, it's called yes, I heard it in the back there, a black hole. So if you wanted to escape a black hole, you'd have to be outside of it. Because if you're inside of it, then the escape velocity is higher than the speed of light. Then nothing, not even light, can go faster than the speed of light. So even light doesn't leave it. So in speed of light, we use the little formula c, a little variable c, and we plug it on here. We get c is equal to the square root of 2gm over r. The two variables now, because that's a constant, the two variables are m and r. This is the radius of a black hole. Let's solve for that. So we have to square both sides. We get c squared is equal to 2gm over r. And then solve for r. We get r is equal to 2g over c squared times the mass. Interesting. Fantastic formula. And that is the radius of a black hole, also called the Schwarzschild radius. Just Googled it for you. Here we go. Radius of black hole formula. We can see that it's R is 2mg over c squared. M is up there, the mass of the object. And it's also called the Schwarzschild radius. Beautiful physics. We're hitting upon some good astronomical physics. Love it. Here's the jingle.